How do ML algorithms mitigate overfitting and underfitting? Imagine trying to teach a robot to recognize cats. If it memorizes every single cat picture, it might struggle with new ones. That's overfitting. If it doesn't learn enough, it can't tell cats from dogs. That's underfitting. Balancing these two is key in choosing machine learning algorithms. When selecting algorithms, understanding how they handle overfitting and underfitting helps you get better results. Some algorithms are naturally prone to overfitting because they can model complex patterns, like decision trees. To fix this, you can limit how deep the tree grows or set a minimum number of samples for splitting. This keeps the model from becoming too detailed and memorizing noise. Other algorithms, like linear regression, tend to underfit if the data is complicated. To improve this, you can add more features or use polynomial regression, which adds curves to better fit the data. But be careful, adding too many features can cause overfitting, so you need to choose wisely. Regularization is another tool. It adds a penalty to the model's complexity during training. For example, L1 regularization, also called lasso, pushes some coefficients to 0, effectively removing irrelevant features. L2 regularization, or ridge, shrinks large coefficients, making the model simpler. Both methods help prevent overfitting by discouraging overly complex models. Cross-validation is a technique where you split your data into parts, train on some, and test on others. This process shows if your model performs well across different data sets. If it does, it's less likely to overfit. If performance varies a lot, you might need to simplify your model or gather more data. Training data size also matters. More data helps models learn true patterns instead of noise. Feature engineering, which involves selecting or creating meaningful features, can improve model performance. If features are relevant, the model can learn better without overfitting or underfitting. Early stopping is especially useful for neural networks. It involves monitoring the model's performance on a validation set during training. When the validation error starts to rise, training stops. This prevents the model from becoming too complex and overfitting. Ensemble methods combine multiple models to improve results. For example, random forests use many decision trees and average their predictions. This reduces overfitting because it balances out the quirks of individual trees. Boosting methods like gradient boosting focus on fixing errors from previous models, which can also help control overfitting. Dimensionality reduction techniques like principal component analysis simplify data by reducing the number of features. This makes models less complex and less likely to overfit. Dropout is a method used in neural networks where random units are turned off during training. This forces the network to learn more robust features and reduces overfitting. Choosing the right machine learning algorithm involves understanding these tools and techniques. It's about finding the sweet spot where the model learns enough to make accurate predictions, but not so much that it memorizes noise. This balance ensures your AI systems, whether they generate images or predict trends, perform reliably across different situations. Properly managing overfitting and underfitting keeps your models trustworthy and effective in real-world applications.